Okay, hello to the members and supporters of the British Museum. My name is Carl Heron. I'm Director of Scientific Research, and I lead a team of scientists at the museum, and we are dedicated to studying objects in the collection from a scientific perspective. We use a variety of different analytical and imaging techniques to study the collection. We also support the care of the collection, and we're dedicated to reporting our findings and our results to the widest possible audience. So thanks to the membership team of the museum, they have conveyed some questions that members of the museum have asked, and I'm going to do my best to go through and answer those questions. There aren't too many of them. Some of them I will probably take much longer to answer than others. So the first question is as follows. My daughter is interested in a career at the museum. What would you study to work in scientific research? So I think there are two ways of undertaking study at university that might lead to a position in a museum. So my own background is in archaeology primarily. I specialized in scientific investigations in archaeology. I wanted to go to university and learn more about human history, about people in the past and how they interacted with their environment, with materials, how they transformed materials and how they used materials and so on. So I wanted a really firm grounding about the history of humans on the planet. And I got that. It was a fantastic degree, but it also had a lot of science in it. It had physics and chemistry and maths and biology. And so it provided me with a good training in the interface between archaeology and the sciences. And I went on to do a PhD and further training and research in those sorts of areas before I went to university and became an academic and ended up in the museum, in the British Museum in 2016. So the other approach, I think, the other direction is perhaps to study one of the sciences first, one of the fundamental sciences such as chemistry, physics, or biology. All of those subjects fit perfectly into training in science in a museum context, in the cultural heritage context. Firstly, those subjects, you learn a lot about the nature of the world, the physical and natural world around you. You learn about the study of matter and how matter is transformed by chemical or biological reactions. So that they're absolutely essential, really, to understanding science at a fundamental level. It's possible also to do applied sciences, such as environmental science, forensic science even. All of these subjects give a good grounding of scientific principles, but also applied in certain contexts. With museum work, one needs to have a really intimate knowledge of materials, of objects, and how people manipulate materials in their environment, whether to smelt metals or to manufacture pottery vessels or to procure food or to make tools and weapons and so on. It really does help to have an understanding of material and of material science. And I would say specialize at a later period. One can go on and do postgraduate degrees where you specialize a little bit more, then a PhD where you really take on a specialist subject in detail. And then ultimately, let's hope that a museum science career beckons for you in the future. Okay, second question is, how do you use science to work out the age of an object? So there's quite a few hours of lectures behind that sort of question. I'm going to say a little bit about one of the most widely used scientific dating techniques, and that's called radiocarbon dating. I think most of you will have heard of radiocarbon dating. And it was first applied in 1949, so just over 70 years ago. And it was applied by an American scientist, a chemist called Willard Libby. And Libby had worked actually on the Manhattan Project in the Second World War, and he applied his knowledge of physics and chemistry and of radioactivity to the potential of radiocarbon as a dating method. First published dates, the first dates appeared in 1949, and he received the Nobel Prize for chemistry in 1960. Now, the technique is based on the decay of a radioactive form of carbon known as carbon-14. So the most abundant form of carbon in the world is called carbon-12. there's a little bit of carbon-13, and then an ever smaller, tiny fraction of carbon is carbon-14, the radioactive form. The other two forms, the carbon-12 and carbon-13, are stable. They're not radioactive. Now, carbon-14 is produced in the upper atmosphere. I won't go into the details of that, but cosmic rays are involved. And once formed, that radioactive form of carbon, it readily combines with oxygen to form carbon dioxide. And carbon dioxide is absorbed by plants. So plants absorb carbon dioxide, they assimilate it, and they convert it into glucose, into the building blocks of the plant's physiological processes. So it becomes incorporated into the tissues of the plant. Animals eat plants, some animals eat other animals and plants, and so that carbon-14 can become distributed throughout the living world, also into the oceans through a slightly different process. So when the organism dies, no more carbon dioxide is absorbed, so none of the stable forms of carbon nor of the radioactive forms of carbon are absorbed. And that radioactive carbon-14 will start to decay. And we understand through the work of Libby and others that carbon-14 decays at a set rate. It will decay, half of that carbon-14 will decay over a period of 5,730 years. So after 5,730 years, half of the carbon-14 has gone. In another 5,730 years, half of that remaining carbon-14 has decays to nitrogen-14, and so on. Every 5,730 years, half of the carbon is decayed. So it's possible, by measuring the amount of carbon-14 in a sample, it might be a sample of bone or a sample of wood, for example, it's possible to arrive at a date for that object, because you know how much carbon-14 is remaining. You have to measure it. You need sensitive equipment. Today, normally, mass spectrometers are used to measure the amount of the carbon-14 isotope. So you can work out the age of a particular sample. So it has to be from a living organism, a bone wood. It can be shell, for example. There's a wide range of organic material that can be dated, but it must be something that exchanged radioactive carbon with the atmosphere during its period of life. Now, there are some complications. I won't go into too much detail about the complications, but one notable issue is that the production of carbon-14 in the atmosphere has not, throughout history, been a constant. For a number of reasons, it changes. The amount of cosmic rays reaching the Earth, for example, the Earth's magnetic field interacts with that. So there's a whole range of reasons why the production of carbon-14 over time, over human history, has not been constant. And therefore, carbon-14 dates have to be calibrated by knowing the radiocarbon date of materials of known age. And one of the most common materials of known age are trees with tree rings. And where those tree rings can be dated, one can have an independent method of arriving at an age of a piece of wood. So if that piece of wood is then sampled, one can measure the radiocarbon age of that sample. If you do that multiple times over in different places at different periods in the past, one can build up a calibration, a correction factor, if you like, that can be applied to unknown samples. So radiocarbon samples are always a range of a statistical range of possibility. So there are errors associated with every radiocarbon date. Nevertheless, radiocarbon dating has absolutely revolutionized archaeology and other subjects as well, but in particular archaeology. Now, the final thing I want to say about radiocarbon dating, it works well up until around 50,000 years in the past. After that, after about 50,000 years, it's really difficult to measure the amount of radioactive carbon that's left because of these progressive half-life radioactive decays of the radiocarbon. There's so little radiocarbon left that it can't really be measured reliably, even using very sensitive mass spectrometers. And therefore, beyond 50,000 years, how do archaeologists and paleontologists, how do they date materials of interest? How do they begin to establish reliable chronologies for the history of humans, the history of other organisms prior to, after 50,000 years? And there are actually a wide range of other scientific dating techniques that are used. Just to name a couple of them here, there's thermoluminescence, uranium series dating, amino acid racemization, potassium argon dating, the whole range. They don't necessarily all work on organic material. Some work on inorganic crystals, on inorganic materials generally. And so that's about it really with radiocarbon dating. There's tons of resources on the internet about radiocarbon dating. There's a whole series of radiocarbon laboratories in the UK, and they all have websites that tell you a little bit more about the dating technique and how it works, and in the circumstances where it might not work. One of the biggest issues around radiocarbon dating is contamination. So the laboratories that process materials for radiocarbon dating, they have to be really careful that there's no modern carbon with its own burden of radioactive carbon associated with it, or else the date will be wrong. So that's something that we all have to be very careful about. Okay, next question. What has been your most exciting discovery in the department? So our department is scientific research, and this year, 2020, we're celebrating 100 years of scientific research at the British Museum. Research laboratory was established in 1920 by a chemist, and 100 years later, we're still generating results and supporting the museum in a number of different ways. So over the years, numerous scientific investigations have been undertaken, and a lot of those have brought to light really important information about objects in the collection. Now, I've only been in the museum for 4 years, so I'm going to give an example from my period in the museum from 2016. And I'm going to talk about somebody else's research, as I often do. And I'm going to talk about one of my colleagues, Rebecca Stacey, who works on trace amounts of organic material, and she uses molecular-based techniques to identify molecules that have survived over long time periods, archaeological time periods, not radioactive carbon in this case, but carbon-based molecules. And those carbon-based molecules can be pinpointed, tied down to a very particular source. And in this case, Rebecca was working with chemists, with scientists at the University of York, who also specialize in the analysis of trace organic material. In the case of this particular project, Rebecca was interested in the contents of ceramic jars. And these are very distinctive ceramic jars. They date to the late Bronze Age period in the Eastern Mediterranean. The particular jar type it's called a base ring juglet, and it's about 15 centimeters tall. Decorated, and these were circulated around the Eastern Mediterranean, I think around the late Bronze Age, so about 1200 BC. And for some years, archaeologists have been very interested in the shape of these ceramic jugs. They look like an inverted poppy head from the opium poppy, and archaeologists dating back to the 1960s had suggested that they may have been used to transport opium around the Eastern Mediterranean. We do find traces of poppy seed, for example. So it's not entirely unexpected that psychoactive substances would have been transported and used during this period. So Rebecca and her colleagues set out to try and test this question. They took a tiny sample of organic material that was a residue in the base ring juglet. And they developed a really elegant methodology, a set of methods to identify the organic molecules in the particular residue. So they did find alkaloids. Now, alkaloids are a specific class of molecule. Alkaloids consistent with the opium plant, with the opium poppy capsule. And they published that. They published that in 2018 in an analytical chemistry a science journal called Analyst. It's the Analytical Chemistry Journal of the Royal Society of Chemistry. And the reason why I like this work is that it combines a really elegant scientific approach, a new methodology, with a robust archaeological question, an archaeological question that they were trying to address, to test and to evaluate. And it also was widely reported in the press. So it has a scholarly interest, but it also has an interest more widely about the use of organic substances thousands of years ago, their survival, and anything we can shed light on these particular ceramic vessels that can help understand them in their particular historical context. Okay, next question. How do you decide which objects to X-ray, and can it cause damage to the objects? Okay, so X-ray imaging is really important in the British Museum, in most museums, in actual fact. So X-ray imaging was first used in the museum towards the end of the 19th century, remarkably over 100 years ago. So X-rays were first discovered by Wilhelm Röntgen in 1895. Within a year or two, they were being portable X-ray systems were being taken into museums. And in this case, the British Museum in 1899, some mummified animals. In fact, a mummified baboon was imaged using X-rays, and the image still exists. Was published in 1902, I think. And ever since then, X-ray imaging has been really important to museums. We can use X-rays to penetrate objects that we can't see inside. The mummified animal, for example, is a great example to test whether the animal is in there, what state it's in, whether there's any pathology associated with that animal. We can ask a lot of questions, and we don't have to do any damage to that object. We don't have to. We certainly wouldn't unwrap the wrappings on a mummified animal. We want to use techniques that don't harm the objects, but we can still study them at the same time. So how do we decide? We might decide because it's a research question. If we're trying to understand animal mummies, might be a good example, and pathology of animal mummies, we would want to X-ray image as many animal mummies as possible in order to get an understanding as to the potential causes of death and the prevalence of disease or whatever the question is. So research is very much one of the reasons why we decided to subject objects to X-ray. The second is a collection care question. It's where we are trying to care for the collection. We want to understand the condition of objects in the collection. Then we would apply X-ray imaging in that sense too. So if, for example, we are exhibiting an object in a gallery, or we're loaning an object to another museum, we might undertake X-ray imaging before that object is loaned. We want to understand the condition, and we want to take decisions as to whether we should loan that object or not. And if an object returns from a loan, then also we may want to do X-ray imaging to test whether that object has been subject to any damage during transit, for example. It's very rare, it's really unlikely, but nevertheless, we have those facilities in order to answer those questions about the care of the collection. So we take an informed perspective, and we want to try and monitor very carefully the condition of objects in the collection. So I think it's two reasons why we apply X-ray imaging research. We want to ask new questions. We want to find out new things about the collection, and we want to make sure people know about that. And secondly, we want to care for the collection, and so we want to have as many techniques at our disposal to help us to do that. Okay, the second part of the question, I'm taking longer than I thought, is can it cause damage to the objects? That's a really interesting question, because certain X-rays, energy of certain X-rays does mean that it can cause damage to objects. And one of the ways in which X-rays can cause damage is to DNA. So DNA can be preserved over archaeological time periods, and we often study ancient DNA, not necessarily us, but other laboratories, universities and other museums are really interested in the study of ancient DNA for a whole host of reasons. And if we or somebody else applies the wrong kind of X-rays, or the dose is too high, then we could damage the DNA in those samples. So a lot of research has gone into how we might put filters on the X-rays, how we manage the dose that we give to X-rays. We might ensure that certain X-rays of a certain energy only are incident on a particular sample. So there's a whole range of recommendations that we could make. And we have to test that out. We do have to test. I mean, science is not just about throwing our weight at the objects in the collection from an analytical or an imaging point of view. We have to do lots of experiments. We have to understand how different materials behave under different circumstances. And so we might do lots of tests first. And Dan, who runs our X-ray facility at the museum, he does a lot of experiments before he applies X-rays to objects in the collection. And most recently, he was looking at pigments, colored objects. And he took some materials and he coated them with different pigments, paints, in effect, colors. And then he irradiated those with X-rays, different energy for different time periods, etc. And he wanted to look at whether the X-rays had any impact on the fading of color of different from arising from different types of pigments. And through that work, it gave him confidence as to how he could apply the X-ray imaging technique to objects in the collection without doing damage to them. So potentially it can cause damage. So again, a really good point to discuss, but we have ways in which we will do experiments, tests, we can make recommendations before we actually use techniques like X-ray imaging. Okay, next question. Have there been any major developments in techniques that have changed your understanding of an object? I think I'm going to stay on the X-rays for a moment. So in 1899, the X-ray systems were pretty basic, I have to say. And over the decades, X-ray imaging technology has improved remarkably, and we have all sorts of methods now that ensure speed of operation, resolution of the techniques that we use, digital capture, for example. But one of the big revolutions in X-ray imaging has been CT scanning, and you'll know of CT scanning from a medical context, and we can use CT scanning in museums as well. And we have our own CT scanning facility at the British Museum, run by Dan, and Dan does a great job. And he's been CT scanning a whole range of objects, organic, inorganic objects, including mummified animals again, and not just taking like a two-dimensional X-ray, but through CT scanning, you can build up a 360-degree investigation of a particular object. And also you can use the penetrative power of the X-rays to look at tomographic slices through that particular object, looking at the interaction of that material with X-rays. And that helps us to really pick out a lot more information than standard X-raying about the interiors of objects. So we've learned a huge amount about how metals, different kind of metal objects were made. We've reconstructed a lot of the mummified animals in the collection through CT scanning. And I think it's a really important method for a museum scientist today. So I think I'll leave that one there and go on to the next question. Do you work collaboratively with other institutions or external individuals? So the answer is yes. And the study of the opiate alkaloids that I mentioned earlier, that was done in conjunction with the University of York. So we work with a lot of university partners throughout the country, in the UK, but also internationally as well. And we work with other museums. Really, it's really exciting when you start to think about bringing the collections of different museums together. And if you can study them systematically using the same approaches, you can really build up a superb understanding and really disseminate much greater information about collections from more than one museum. External individuals, I'm going to mention the Tahitian mourner's costume that was on display in the museum in 2018 to 19. And this was part of the Reimagining Captain Cook exhibition. It was a fantastic free exhibition at the museum. And the centerpiece was the Tahitian mourner's costume that was collected by I wish I had some pictures to show you, collected by Captain Cook in the 1770s, probably on his second voyage. And it's a wonderful costume. It's a composite costume with bark cloth, with a wood, shell, feather, composite materials in this wonderfully ornate and elaborate costume that was used in some mourning rituals on the island of Tahiti in the South Pacific. And before it went on exhibition, before it went into the exhibition in 2018, there was a very long period of conserving the objects of the part of the costume. And also we did scientific research. So we did a lot of new investigations that are just now being published and reported. We did a film which you can find on YouTube. And I do recommend that you watch that because it provides fascinating context to this particular costume. So how do we collaborate with other institutions? At the end of the exhibition, the curator for the exhibition went to Tahiti, and she is a specialist in the history and archaeology of Oceania, where Tahiti is located. And she also went with a conservator, so had an intimate knowledge of the materials from the costume, and a scientist who had conducted scientific analysis of some of the materials in the costume. And the three of them were there to share information with the Tahitians. So there's a national museum on Tahiti. They gave talks and had lots of interactions with people who are using materials today. I mean, there are no mourners' costumes used on Tahiti today, of course, and very few in the world left. There's only about a dozen of these costumes known throughout the whole world. And so part of the trip was to share information with the Tahitians, but actually it was a two-way exchange. And this is really important because the scientists and the curators and conservators were learning about materials within the natural environment of Tahiti. So it really informed our work that we've been doing on the costume, and it builds a relationship which we hope will be sustained in future research programs, exhibitions, and so on. So it really provides that platform for understanding our collection and sharing our collection and working with external individuals. So I think that's probably one of the most enriching parts of our work, is to work with other specialists, but also other communities around the world. Okay, is there anything in the collection you are dying to research, but it's too delicate to do so? I'm thinking in the same way they won't open the first emperor of China's tomb until they have more advanced equipment. Okay, so that's a difficult question. There's so much material in the British Museum collection that it could support 1,000 research projects, and yeah, it's. I'm going to say the Lewis chess pieces. I'm very keen on supporting research in the new research into the Lewis chess pieces. These are these amazing chess pieces dating to the late 12th, early 13th century AD, and they were found on the island of Lewis in the Outer Hebrides, and in 1831, I think. And there's quite a lot of pieces. It's more than one chess set. There's, I think, about 80 or 90 chess pieces, and they're beautifully carved. And they're carved mostly from walrus ivory, from the tusks of the walrus, the enlarged canines. And the walrus ivory probably came from Greenland, although we haven't tested that out scientifically. That provides one question that would be nice to address and to answer. So geographical origin, where did the Lewis chess pieces come from? How were they carved? What tools were used to carve them? What was the technology of their production? What part of the tusk of the walrus was modified in order to shape the pieces? And also there's been some suggestions in previous investigations, not only conducted by us at the British Museum, but there are pieces at the National Museum of Scotland as well. And there's been suggestions that the chess pieces were that color was applied, that pigment or paint was applied to the chess pieces, and there were traces of mercury, I think, which could come from the pigment cinnabar or vermilion, and it would be really interesting to apply new scientific approaches, imaging techniques. For example, we use multispectral imaging, looking at the interactions of light, of different kinds of light, and the reactions of surfaces to that light. And it would be possible to, I think, reconstruct the color that was applied, the pigments that were applied to the Lewis chess pieces. We could also work with external partners to understand the geographical origin. So the chess pieces stylistically, it's thought that they might have been carved in Norway, because they have a lot of associations with Norwegian styles of carving from the same period. But so there's lots of questions, and I just wanted to reiterate that the museum collection we never finish research. So objects that scientists in the past and curators and conservators have investigated years ago, because of advances in techniques, in scientific investigation, advances in our thinking, our understanding of these different objects in the collection, we always want to revisit. We always want to bring new approaches, new thinking, new techniques to those objects in the collection. So we never finish with our research. Ultimately, we want to, again, share as much of that as possible. So that's the 7 questions, I think. I hope I've answered them, and it's been an interesting a few minutes that I've spent with you. I'm talking to you from my kitchen table, from my kitchen in Yorkshire during the period of museum closure due to the coronavirus pandemic, the laboratories are currently closed. The museum, of course, is closed. And scientists are really keen to get back into the museum and get back to the laboratories and continue with their projects. But do keep in touch, members of the British Museum and supporters. Thank you for all the support that you've given to the museum. We will keep producing resources, films, newsletters, articles, and so on. And I hope you're able to keep up with what we're doing. So thank you very much for listening, and goodbye.